If you consider the finite thickness, in other words, if you bring the third dimension of the layer of the fluid, you can get a correction down here which starts to make this and this look more alike. But the physics has nothing to do with the structure is similar, but the physics is completely different. You will note, as we were discussing, both these waves are non-dispersive. They are dispersive, but this wave is, I would say, strongly dispersive. And this wave, I would say, is weakly dispersive, especially at long wavelength. Right? In other words, at k per rho squared, much less than 1, this starts to be pretty dispersionless. Okay? The other thing is, of course, that both there are special, as I say, you would not describe zonal flows. We'll come to that later in our lecture series. You would not describe zonal flows with the Hasegawa-Mima equation, but nevertheless, both have the possibility of symmetric zero frequency solutions. In other words, here it would be kx for the qg, and it would be ky for the Hasegawa-Mima solutions. So there's a hint, certainly, of zonal flows here. Okay? One important thing about drift waves is they propagate radially and toroidally. Toroidal means in theta. So the radial group velocity, which will make its appearance again, is minus 2 kr k theta rho s squared v star over 1 plus k perp squared rho s squared squared. So there's a radial group velocity, which means there's a radial wave energy flux, which is something that's very important. And speaking, does this factor remind you of anything? Kr, k theta? Hint, it's on the board somewhere. We talked about it earlier.
Reynolds drive.
Exactly, it has exactly. So there is a connection between the radial wave propagation and the Reynolds stress. We will keep that in mind for later. That's why I make this point. Very important little point to keep in mind. Okay, so you have symmetric solutions, you have radial propagation, you have all sorts of goodies. That's, of course, they propagate toroidally as well. What other basic features do we need to talk about here? All right, so we want to talk about instability. So, the basic, again, the drift wave coming from the Hasegawa-Mima model, right? There is no grad n driven instability. Right, and again, let me remind you, you can see that because the particle flux is rigorously zero with Boltzmann electrons. So if there's no particle flux, you can't relax the density gradient. You can't relax the density gradient, then there's no way you can tap the free energy source in the density gradient, and no chance to get a density gradient driven instability. So, for what is called a drift instability, what you need is you need to keep some kind of correction to the Boltzmann response. So you need n over n naught now to be equal to E phi over t plus some non-Boltzmann response h. So there are two ways of doing this. The boring way and the, I think, easier illuminating way. The boring way would just be to plug into the Hasegawa-Wakatani model and crank it out. The clever way would be to realize that, in linear theory, I need Ni over N naught is equal to Ne over N naught. Okay, and now let me continue over here. So we know that Ne over N naught is going to be E phi over T plus H. And we can put this as K and K. And we know from doing our Hasegawa-Nema studies that Ni over N naught is equal to omega star E over omega minus K perp squared rho S squared times E phi K over T. Right, that just comes, you could think of that in just solving the equation for, the equation for dNi dt, plugging in the E cross B, the polarization drift, okay? So that's just the response, right? So the question is, what we need is an equation for this guy, right? Well, lo and behold, our friend the Hasegawa-Wakatani equation solves that, because what this equation is dn dt, d by dt of n tilde over n naught, plus v star d by dy of E phi over t. And then we have our friend over here is equal to minus d parallel del parallel squared of now E phi over t, just writing it all out, minus n tilde over n naught. Right? So you notice what I can do is I can write Ne like this. This thing just becomes my friend H, right? So this thing becomes plus d parallel del parallel squared H, right? This guy becomes d by dt of E phi over t plus H. Right, and this guy becomes v star d by dy of E phi over t, right? So I can rather sneakily write this as d by dt of h minus d parallel del parallel squared of h. And this thing I can bring to the, this is a plus, I can bring to the other side. I can write this as a minus d by dt. Now, minus let me write it this way, d by dt plus v star d by dy times e phi over t. And notice this is exactly what the doctor ordered, right? Because this allows me to compute h in terms of e phi over t. Right? So you'll notice that this we can write then in Fourier space as minus I omega plus d parallel k parallel squared acting on h of k is equal to minus e over t, and then there is an I there of omega minus omega star. And do I have my signs right? I have a minus there and a minus there. So I have a minus, well, hang on, I have this. Hang on a second, I think I have a sign flip somewhere. These two should be opposites. So this is this is all right for the moment. So there's an I there. And I pull, that's a minus I, and I pull this out. Yeah, I think this is all right. Yeah, there we go. Omega minus omega star e phi over t. Okay? And I can further pull this guy out and put an I there. Now you see, the point is, this is the thing that's going to produce instability. Why is that? Like, that's the critical term. Why is that? Because that's going to give you the shift in the phase between the density and the velocity, right, or the density and the potential to create a non-zero particle flux. The non-zero particle flux then relaxes the density gradient, and of course the fluctuations grow. Okay, we'll show that from energetics too. Okay, but here, this is the critical thing. All right. So I still have some space here, so I can use it. So you notice I can, write h tilde of k, then is minus e over t, omega minus omega star times phi, over omega plus I k parallel squared b parallel, right? So now we're rolling along here, right? And we have the minus sign sitting there. Well, then for the instability that we want to talk about, right? So I still have more space. Right, I can probably get this in here. I just put 1 minus, I factor out the e phi over t, so I would factor out 1 minus omega minus omega star over omega plus I k parallel squared b parallel. Let me put this in like this. And this has to be, this is just NE, this has to be equal to NI. And then this thing is equal to omega star over omega minus k perp squared rho squared. Okay. Right, and that's kind of our linear instability condition. Okay, now to make further progress, we need to do a few things. In the limit of omega over k parallel squared b parallel, much less than 1, which is 1 over the thing being larger than 1, we can treat this side as a kind of perturbation. So to lowest order, we balance these two things. So the 0th order frequency, omega k, is just equal to omega star over 1 plus k perp squared rho s squared. So it says that for strongly, for strong, not Boltzmann, but strongly adiabatic electrons, the basic wave is the case you get out of the Hasegawa-Mima equation. Now, for the correction, then what we do is we balance basically the correction to this term with this. So in other words, what we write is minus, if we call this omega k 0, we write this as minus omega k 0 minus omega star over omega k 0 plus I k parallel squared d parallel. All right, and this has to be equal then to the first order bit in this thing, which I'm going to write it as omega star over omega plus delta omega and expand. So I'm going to write this as minus omega star over omega squared delta omega. Right? And delta omega, the total frequency is omega k 0 plus delta omega k. Delta omega k is the correction, the piece that gives you the instability. So in some sense, a drift instability is a drift wave with a kind of destabilizing dissipation embedded in it. One of the interesting things, ultimately, the thing that produces the instability here is the parallel diffusion. In other words, dissipation produces the instability. That may be a little counterintuitive to you, right? Usually you think of dissipation or diffusion as stabilizing, right? Here it's destabilizing, and the reason is shifts the phase between V radial and N in such a way that the density gradient can relax. Okay, we'll show that. So anyway, just to finish the algebra. So in the limit, again, we're in this limit, so we can drop this guy here. All right, so we have this. Right, and then we can bring him upstairs. So we have minus I times omega k 0 minus omega star over k parallel squared d parallel times omega over omega star equals delta omega k over omega k. And here is our story. You notice we have minus I times omega minus omega star. So a condition for instability is, since this is negative, right, you want the whole thing to be positive for instability, is omega be less than omega star. So you need omega less than omega star. And that is indeed the case, right? And that's the important effect of our friend, the polarization drift here. Okay, so very important. So you can then, the algebra, not enough space on the board. Right, so you're pretty much done here. Now you can kind of regroup the things. You realize that delta omega of k over omega k is equal to gamma of k over omega, so that's calculating the effective growth rate. And then, so let's just plug in the pieces here. What do we have? We have I times omega star minus omega star over 1 plus k perp squared rho s squared. Then the whole thing is divided by k parallel squared d parallel, and then we have this other cheerful factor of omega over omega star, which is just an additional thing of 1 over 1 plus k perp squared rho s squared. And we can kind of regroup the whole thing as I times omega star over 1 plus, I times omega star over k parallel squared d parallel. So there's our effective. And then we have various factors related to growth. So we have something like k perp rho squared over 1 plus k perp squared rho squared quantity squared. And there, this is, let me write it over here, is our, simple, we don't need the I and the gamma here. So I, delta over omega, so I equal I gamma, so we do this, so then we can just write this. There we go. That is our simple drift instability growth rate, right? That is called the collisional drift instability, and that goes back to the 60s, actually, if I say it. Is it blast off time? All right, let me just finish this phrase and we'll get out of here. So anyway, you will note that, this thing, has a character. If I didn't worry too much about these factors, this factor is important, right? Because this comes from the omega minus omega star, okay? If I didn't worry too much about these factors, the typical growth rate would go as omega k over k parallel squared d parallel times the wave frequency, right? And this is a generic form, right? So this is, this is in some sense a measure, this is in some sense a measure of the size of h bar, right? H hat, and h hat is the non-adiabatic electron response, which is essential to produce the instability, right? So it says basically, the growth rate, you know, another way to say it is the ratio of the growth to the frequency is in some sense related to the frequency times the parallel diffusion time, right? Or the time over which the part, say an element of fluid, experiences dissipation. So that's a generic trend in drift waves. So I think next time, even though we're supposed to move on with wave turbulence, this is pretty fundamental, so next time I want to say some more about this and more about the kinetic theory of instabilities, because it's fundamental material. So we'll continue with this next time. Anyway, that's the drifting stability, okay? And, you know, as I think an interesting homework exercise would be for you to try and calculate the quasi-linear particle flux now for the drift instability. So why don't you try and calculate this? There's a lot more to be said about these basic things, but anyway. Any questions? We have to call it quits early today, so. You guys look like you're exhausted. You've covered quite a bit of material.
Where does the non-adiabatic term come? Or how can we calculate it?
How can you calculate this?
No, I mean the non-adiabatic term in the left,
Where?
the upper one.
The here?
Yeah.
No, this is, Ni is this is the one. That's the adiabatic bit.
I mean the non-adiabatic part of the electron density. Yeah.
I didn't, the non-adiabatic part is the H. That's what we calculated.
I mean how is.
How do we calculate it?
Yeah.
Well, okay, I showed that. I mean, you realize that you can write one of the Hasegawa-Wakatani equations, you can convert it from an equation for N to an equation for H, right? Which is this. So, right, remember this, you know, you have dN dt, so you have d by dt of phi plus H by definition, and then B cross B dot grad phi is equal to 0. So you immediately convert it to an equation for H, so that's this. So what we did was we solved this equation to relate H to phi. And that's where this comes from, okay?
So you solve that from the first equation and then take it into the second one because of instability.
Exactly. All I did in other language, though, I mean, I think the right way to think of it is not into this equation, that equation, is I calculated, you know, I know I know the adiabatic part of the electrons. I calculate the ion response, I calculate the electron response, and I equalize them by quasi-neutrality. And that's all I did here in the end.
And the physics, the picture is that the damping of the density along in the parallel direction, the energy goes to the electrostatic potential.
Exactly.
Okay.
Exactly. But why? I mean, that's an important point. You're getting the message, because the idea of damping making fluctuations is a little counterintuitive, right? And the point is, the answer, I've said this twice. Well, it's not just Landau.
Okay.
Landau damping would give you damping of fluctuations. It's inverse Landau damping. And the point is, it's this omega minus omega star factor is negative, so it flips the sign. That's absolutely essential. So it's Landau growth, not Landau damping. Okay? And the physics of it is that that little dissipation shifts the phase of N and phi such that you get a particle flux. And that the fluctuations grow from relaxation of the density gradient. okay?
The C shift and the phase is kind of mathematical.
Yeah, but I mean, but you see the point though. I mean,
Yeah.
the point is that you have this nice free energy source, right, grad N, right? And you'd want to relax grad N. So the entropy production, think of it in terms of entropy production, would be something like minus the particle flux grad N. So that would be, this is the flux and this is the thermodynamic force. You need the phase shift to make the flux non-zero. That's the point. Otherwise, you can't access the free energy. And you need two things, by the way. You need the dissipation, and you need the omega less than omega star. And this will become clearer when we talk about the kinetic version. So it's an interesting thing. It's dissipation triggering instability. Right? Those of you who may have encountered the tearing mode in resistive MHD, it's somewhat similar. The free energy source in the tearing mode is the current gradient, but the trigger is the resistivity. Okay? All right, we'll see you tomorrow then. Not tomorrow, Thursday. We'll talk some more about this, even if we slip a little bit on the schedule. I'll be